All right, we are live. We had some technical issues, that's why we are a little bit in late, and still we are fixing some issues. So I will not give an introduction because of the technical issues, but I will leave the word immediately to Tom, who will present the winning solution on his latest Kaggle competition. Tom, it's all yours.
Great. Right, so this presentation is about shared work with my fantastic teammates, Dimitri and Ara. They're also in the audience today. Dimitri is currently ranked 5th globally in the Kaggle rankings, and Ara is a work colleague who was a Kaggle novice at the start of the challenge. This will not be an exhaustive presentation, since we tried out way too much to cover comprehensively. The presentation will zoom in on the areas of the challenge that I know best, and there should be plenty of time at the end of the session for questions. At that point, you can also direct your questions at Dimitri and Ara. And I would like to quickly introduce myself, Kaggle, and my Kaggle journey before diving into the challenge and our solution. Right, so maybe a quick note to Sam. Perhaps on the StreamYard, you could just show me and not the others, since I'm having some feedback. Right, so my background is in computer science, specialized in AI. When I graduated in 2010, Sophie and I, we moved to Australia. We had 2 years not working. And then coming back to Belgium, I started working at a chemical plant in Ghent, Eastman. And after a year or so, I realized I needed some more data fundamentals. So I started studying statistics on the side. Shortly after graduating in 2016, I joined DeepMind, where I spent 2.5 amazing research years before moving to Norway, where I'm currently working at Intellisy, a Norwegian startup. So Kaggle, for those of you who don't know, they brand themselves as the home of data science, and they have been organizing machine learning competitions since 2010. Originally, it was all about competitions, but gradually there has been a widening of the scope to cover all data science aspects. One such example is the introduction of free courses in 2018. Originally, the competitions were all about submitting predictions. So you would typically submit CSV files, which would predict on a static data set. And since 2016, there has been a shift towards code competitions. So here you still get evaluated against a static data set, but your submission is now code, which makes it more fair because you can constrain the execution time. And since 2020, there has been a really exciting evolution because now you still get to submit code, but you get evaluated on a dynamic environment. This makes it compatible with the reinforcement learning framework and allows for much more interactive challenges. Sadly, the topic of today is a classic old school predictions competition. So let me take you on a quick historical journey of my Kaggle experience. An important milestone took place almost exactly 5 years ago when Jonas de Grave gave an amazing presentation on this forum, the Ghent Data Science Meetup. And if you haven't seen it, it's an amazing presentation on deep learning and how his team won a plankton competition. My first non-playground competition was about using phone data to predict the location of the phone. It sounds quite similar to the topic of today. And I managed to win. And after that, I helped the bank predict what products a customer would buy. A couple of years later, I tried to predict earthquakes. And even though I did quite well, Dimitri, his team, was much better and ended up winning. Next, I won the Halide challenge, which was a multi-agent resource management game. And then came my favorite challenge so far. And it was in large part because of the collaboration with Dimitri. So this was one of the first simulations competitions, and we built agents to play the game of football. And this was evaluated not against a fixed environment, but against other competitors, which made it, a fantastic experience. Next, we decided to team up again, and we helped Santa collect candy. That went well, and in the topic of today, Ara joined the team, and we won this indoor location and navigation challenge. So the goal here is to identify the position of a smartphone in a Chinese shopping mall. It's organized by Microsoft Research, and it's a real-world data set. It's all about smartphone navigation. So all data is collected by Android phones held flat in the walking direction, and it comes from Chinese buildings. So the data set consists of almost 27,000 labeled trajectories. And here you see one such example of a trajectory. So a trajectory is a sequence of waypoints, which are time-stamped. And in what follows, we will call a segment that part of a trajectory which falls between two waypoints. So in total, the data set was 55 gigabytes of uncompressed text data. And this is how the data was collected. So the data collectors, they had to install an app, and then the app would tell them where to go. And when they made it to the pre-described location, they would click a checkpoint button and move on to the next one until they reached the end of the trajectory, and then they would repeat that process. Now, crucially, the waypoints, which this app directs these data collectors to, lies on a grid. So it's not random locations. They are meaningful locations on the floors of these buildings. They can typically be shop edges or corners, which makes it easier to navigate to. And on average, each waypoint is visited 3 times by the different trajectories. So like I said, the data comes in text files, and there are 3 asynchronous data modalities. So the first one is the target data. And on average, you have 1 target waypoint every 5 seconds. And this consists of a timestamp, a building, a floor on that building, and the XY coordinates of the waypoint. And then for the test data, you need to predict the floor and XY coordinates given a timestamp and the building ID. The second data modality is the sensor data. And this comes in at a much higher frequency, about 1 data point every 20 milliseconds. It's 3-dimensional data, and there are 4 different sensor types. First one is the accelerometer. So this measures the forces, the changes in velocity. There's magnetometer data, which measures the magnetic field. Gyroscope, which measures the change in rotation. And then there's a built-in rotation vector. Like at this point, we don't know what it means, but it looks important. And finally, there's the Wi-Fi and Bluetooth data, which comes in at a different format, about 1 data point every 2 seconds. And it has repeated timestamps. And that's because one Wi-Fi observation typically consists of multiple devices, multiple physical Wi-Fi devices. And each of these measurements contains a signal strength as well as a timestamp of when that signal strength was last updated. So on average, there are about 20 to 200 Wi-Fi observations, Wi-Fi devices for each Wi-Fi observation. Now let's zoom out a bit to the trajectory level. So in total, there are 626 test trajectories, which are spread out over 24 test sites. And there are almost 27,000 train trajectories, which are spread out over 204 buildings. And of the 24 test buildings, about 11,000 occur in the train data. Now, if you look at the distribution of the number of waypoints for the train and test data, you will see that the test data consists of much longer trajectories. So here, typically, the average sequence length is 16, and it is at least comprised of 6 waypoints, whereas the train data contains many small, but also some of the longer trajectories. Okay. Now, in terms of the data collection, it turns out that the data collection is time dependent. And also the test data actually comes from the same time distribution as the train data. So it's not like where you have a typical split where the test data follows all the train data. No, the test data is interleaved with the train data. And the data collection itself is time dependent. So here you see a typical example of one person collecting data where each dot is a trajectory. So here they would collect a couple of trajectories, take a break, collect some more, and then eventually move on to the third floor, and so on. So it's important to keep in mind that the data collection has some structure in it. And in Kaggle competitions, you want to do as well as you can, and that's determined with some metric. And here is the mean position error. So as we stated, we need to predict X and Y coordinates of the waypoints, as well as the floor. And the ranking is based on your distance between your prediction and the actual waypoint, plus a constant floor error. And then all of that is averaged over the different waypoints. In this presentation, we will only discuss the coordinate prediction, the XY prediction, because the floor prediction is almost trivial and it's a much easier task. So before we dive into our solution, I would like you to take a couple of seconds and think just for yourself about how you would model this problem. And the dilemma is as follows. You have to pick one of the following 2 approaches. So the first one I would call the deep learning approach, is where you take all of the relevant raw data, pre-process it, and then feed it into like a well-compartmentalized neural network. And then this neural network would predict a sequence for which you know the timestamps of the locations of your waypoints of the test trajectory. The second approach is the engineering approach. And here you would use separate models to model each of these input data modalities, and then use some smart optimization to make your predictions coherent. So yes, please take a couple of seconds to think about how you would approach this. So you only got a couple of seconds. It took us days to figure out, and we couldn't. So we tried both, and it turns out that the engineering approach was a clear winner. So this is the timeline of what we did. The first 3 weeks, we explored the raw data. Then quickly, we built an end-to-end Wi-Fi model from which we got like leaderboard feedback, and we could test the whole process. We built some more Wi-Fi models. Then we incorporated the relative movement data, the sensor data. And after establishing an initial optimization, we iterated on all the components. And we also did a lot of leaderboard probing. So this is something which is not disallowed by the rules. And the idea is to make submissions with the intention to learn more about the test data distribution. So on Kaggle, for those of you who don't know, you only get feedback on the public part of the leaderboard. And the final ranking is based on the private part of the leaderboard. And here, we quickly realized that the test data is split by entire trajectories. So what we did is we modified a reference submission to extract the IDs of the public and the private trajectories. And once we did this, we got a couple of benefits from knowing how this split works. The most obvious one is you can speed up your generation of the test predictions, since you only need to generate your test predictions on a small subset to get feedback. But also it can be used to better understand like the hardest public trajectories. And you could then change your submission just for those. And even though that doesn't change your predictions on the private part, you can hopefully generalize your findings to get better results on the private data. And in what follows, we're going to discuss 7 milestone models and explain how we went from an error of 15 to an error less than 1. So the unit here is meters. So this means we can, on average, determine where you are in the building with an error less than 1 meter, which is pretty amazing. So in these scores, we report the public score, which is typically slightly lower than the private score, but it's well correlated. And the gap, I think, can be explained with 3 main reasons. So the public floor test predictions were crowdsourced, which means that they were perfect. Whereas the private test floor predictions, of course, were like slightly challenging to predict. Also, the private test data contains some of the fundamentally harder trajectories, and there's always the risk of overfitting. So early on, Dimitri made a very nice distinction of the 3 types of model inputs. The first one is absolute position data. So that data which can be used to predict the floor and the XY coordinates. And there are 3 such modalities. What you see here is the Wi-Fi and Bluetooth data. And it turns out that there's much more Wi-Fi data than Bluetooth data. So this plots the number of lines, the average number of lines of Bluetooth or Wi-Fi data for each of the 24 buildings. So there's almost 27 times more Wi-Fi data than Bluetooth data. And it's also of a slightly higher quality, which explains why we mostly stick with Wi-Fi in our approach. The third absolute position data modality is the magnetic field. And even though it looks interesting, we found it hard to get any benefit from it, since it seemed to be time dependent. The second model input type is relative position data. So this cannot be used as a solution by itself, but it can likely improve the absolute position predictions. So what you see here is a picture of the Z accelerometer data, so the force in the Z direction. And you can see that it's centered around 9.81, which is the Earth's gravitational acceleration. And this can be used to see where the person is walking or not walking, and hopefully also to extract other insights, like the distance traveled. The third and last model input type is the trajectory order. So what you see here is one trajectory, which is followed by this one. And we show a plot of the distance between the end of the previous one and the start of the next one as a function of time. This is a log on the x-axis. And you can see that a large part of the trajectories have a distance of 0, which means that the next trajectory starts at the end of the previous one. I think it's about 1 in 4 for which it's exactly the same coordinate. And this next confusing plot really shows the same thing, where every color is a different building. And for the first 20 trajectories of each building, we plot the first point of a trajectory together with the previous last point. And you can see that these tend to move together. It's the same insight as this, but more confusing and more flashy. So before we start modeling, we need to set up the local validation. And in this case, the data size is large enough not to need to go for cross-validation. So what we opted for was to make a holdout set, a validation set, which was as similar as possible to the test data. So we made it similar in size. Like the test distribution, we also restricted to the longer trajectories. All of this is stratified by building and floor, which means that we don't include the buildings which are only seen in training. Now, from the exploratory data analysis, it's obvious that Wi-Fi is a sensible place to start because it allows you to make a submission. It's an absolute position data type, and the raw data is relatively straightforward to interpret, and it would always be part of our final solution. So the first thing to notice is that the Wi-Fi data and the ground truth data is asynchronous. So somehow we need to map the ground truth locations to the Wi-Fi locations, and we just use linear interpolation there. And then what we did is we grouped all of these interpolated coordinates with the signal strength for each of the Wi-Fi devices for all of the floors. So that's what you end up with is something like this, a table of coordinates with signal strengths. And then for each of these devices, we would fit a parametric model, which models this data as well as possible. So we would fit the center of this data, as well as the strength at the center and how it decays as you move away from the center. And you see something like this as a result of fitting such a model. So you would fit the center somewhere and then see a decay as you move away from the center in any direction. And then the prediction would be made by triangulating all of the devices that you would see or not see, and then use that to select the maximum posterior to predict the XY coordinate. And even though it sounded very good on paper, this worked terribly. We only got a public score of 15. And the reason for that is because this parametric approach doesn't fit the data very well. Wi-Fi data is typically directional, and it's highly sensitive to the walls. And it's also highly sensitive to what type of a wall it is. So it turns out to be very hard to model this with a small number of parameters. Right, so what do you do if a parametric model doesn't work? Well, you go non-parametric. And one such example is nearest neighbors training. In non-parametric models, as we show here, they don't include a training phase. They only include an inference phase. So at inference time, what you essentially do is you compare a Wi-Fi observation to all of the Wi-Fi observations seen in training, and then simply predict the location to be the one which is most similar to the one in inference time. And all you need to do that is a distance metric. So Wi-Fi observation, as said before, what is it? It's a bunch of devices with signal strengths. And you need to compare this to another bunch of devices and signal strength. So we did the simplest thing we could think of, which was to compare the shared devices, look at the absolute difference in signal strength, average that, and then add a penalty for not sharing all of the devices. So in this example, 2 of the 5 devices I shared, but at most we could share 3 because the smallest one only contains 3. So that means we give a penalty of 1/3 plus a constant times this average signal difference for the shared devices. And then really our final Wi-Fi model is simply the previous one, where we slightly extend the distance metric to factor in how outdated the Wi-Fi signal is. And then we triangulate by not just using 1 nearest neighbors, but weighted 20 nearest neighbors. We had another pretty good absolute position model, which was mostly Wi-Fi based and resulted in good predictions. So public score of 7, whereas the previous one had 6. The only potential downside here is that it only gives a point estimate. So it's less granular than a nearest neighbor approach, which gives you a full density map. Now let's move on to our initial relative movement models. So we asked ourselves the question, what can you predict with the sensor data? And we settled on a rotationally invariant trajectory. So essentially this trajectory, except for the initial heading. And we thought we could do that because we had the accelerometer and the gyroscope to change the rotation. Right. So we built 2 types of models. One distance model, which takes in sensor data of one segment, and a second model which computes these angles of subsequent trajectories. So the second model takes in 2 trajectories and predicts this angle. And then if you put that all together, essentially what you have is a rotationally invariant model of your trajectory. Now at this point, we could make our first attempt at combining the absolute and relative movement predictions. And since we only consider waypoints seen in training, it is a discrete optimization challenge. Obviously, exhaustive search is impossible since you can have over 1,000 waypoints, choices at each step, and there can be over 100 steps in a trajectory. So what we did is we opted for a beam search discrete optimization. And we'll talk you through this step by step. So for the first prediction, you can only consider a fixed number of observations. And that's what beam 1 determines. So it's set at 50, of which we show the 10 best matches. So here we consider the best 50 Wi-Fi matches. And then for each of those 50, we consider beam 2 next steps. So this is one step into the future. So for each of these 50, we have 8 choices. And these choices are selected with some greedy heuristic. And then for all of those 50 times 8 length 2 trajectories, we update the penalties up to that point. And this is where the reduction operation happens. So you go back to 50. And then the process repeats. So for each of these 50, you consider 8 next steps in this case. Again, update the penalties up to that point and go back to 50. And if you repeat that, you actually have an algorithm which scales linearly as a function of the sequence length. And it works very well on this data. So this should be animated, yes. What you see here on the top left is the Wi-Fi penalties at each step. The bottom left shows the best 10 matches, and the bottom right shows the best match. And in the end, we predict just the trajectory with the lowest overall penalty, and that's it. And that's how we went from a score of 6 to 4. In our code, we use a beam 1 of 2000, a beam 2 of 100. Now, towards the end of the challenge, we realized that we were overcomplicating the sensor models. There's actually no need to make the predictions rotationally invariant, because the rotation vector actually encodes the compass direction, which means you can actually build a model to predict the change in X and Y. And when we did this, of course, like we have much more information, since we can exclude the rotationally invariant alternatives. And then Dimitri did like a massive effort on improving our relative movement models. Really modeling this could be a competition by itself easily. And it was by far the most important component in our optimization in terms of reducing the leaderboard metric. So he did a lot. Some of the things he did was to incorporate the non-test sites. He also modified the training to not include just trajectories of length 1. He used trajectories of longer lengths. Initially, the architecture was just a recurrent network, and now it's a CNN plus GRU stack. He added learning rate scheduling and multiple runs, which start from different random initializations and are then averaged, which reduces the variance of the predictions. Also interesting was to see that sometimes these relative movement predictions can become unreliable because the the phone device is poorly calibrated. And then you would have a period of large errors until it would get calibrated again. And we tried to remove this bias, but that was hard. But we were able to predict when it was uncertain. So actually, we trained the model to predict the absolute error as a function of the surrounding errors, and then use that to modify the penalty in the optimization. So when we were less certain about some of the relative movement predictions, we would give it less weight. Sadly, at this point, we're still occasionally making catastrophic errors. And it makes sense because our optimization only considers discrete choices, and sometimes the test data contains waypoints which we haven't seen in training. And here you see one such example. So the Wi-Fi data in blue says it's here. The actual data is also here. But after we apply our optimization, we're shifted. And that's because we're missing the true waypoints. Another symptom of our approach is shown here. So here you see that the validation error tends to increase as the sequence lengths get longer. And that also makes sense, since you have a higher probability of missing some of the waypoints for the longer trajectories. So like this could also be a competition of itself. It was a massive effort by Ara, who tried to fill the gaps of our waypoint grid. And when we approached this, we figured that false negatives are much worse than false positives. So it's okay to introduce a lot of waypoints, even if none of the data actually occurs in there. But it's terrible not to have a waypoint when there's actually a waypoint there. And the code distinguishes between wall and inner grid waypoints. So most points you see here are wall waypoints. There are some inner grid ones. And it's based on local and global neighborhood statistics. There's also special consideration for corner points, since those are actually very important and need to be injected at a different distance. And finally, Ara applied clustering to blend the generated waypoints to the desired resolution. And in our optimization, we now consider all grid points, but apply some correcting penalties to bias the search towards the waypoints seen in training. And yes, with these changes, we are now at an error of 1 meter, which was quite incredible. Like, we thought initially that the best we could do would be 3 meters, but now we're at 1. And also our validation error is now flat, pretty much flat as a function of the sequence length. So in total, we had 7 different penalties. I'm not going to go into detail here, but this is an example at the end of a trajectory, which summarizes our best prediction, which is a combination of the 7 penalties at the trajectory level. And we would tune all our hyperparameters and relative weights with Bayesian optimization. So this is it. We can now make great test predictions. And this is an example of the plot, an example of one of the plots we looked at for assessing our predictions on the test data. So here you see a floor with the actual and injected waypoints. This is the zoomed in part. Actually, on this trajectory, all our predictions are blue, so they're seen in training. We show the uncertainty of our distance and absolute movement model, as well as the cumulative absolute XY coordinate changes together with the final prediction and the difference between the two over time. So in the end, we had a very hard time deciding what additional grid to use, so these additional red points. And it clearly looked like the most important choice. But in the end, we realized we didn't have to choose. We could just generate different types of additional grids. So here on the left, you see a sparse additional grid. On the right, this one is more dense. And we would just compute the optimization for each of the grids and pick the one with the lowest penalty. So here you see an example of why this is a much better fit for the data, since you only need to inject 1 additional grid point, whereas here you have 3. And it's a much better fit with the Wi-Fi data, this stuff here on the background, as opposed to here. And this is the final ranking. We won by quite a large margin. And in the end, our error was 1.3 because of the XY error and 0.2 because of the floor error. So yeah, thank you for your attention, and special thanks to Sophie for turning a bunch of text into a presentation which was hopefully engaging for you to follow. Let's take some questions now.
All right, so I think for questions, people can use a YouTube chat as well to ask their question, but I see you also have
Thank you, Tom.
Maybe if it's okay, there are some questions from, I'll just start reading them out, right? So from Mathieu, who might have missed the info at the beginning, but how to set up the collaboration, mostly set up everyone in disjoint tasks, or could those be piped together? And how much kind of brainstorm and work was actually split up?
So I think Dimitri had a very good heuristic here. Like, his idea was everyone should pursue what they find the most engaging, the most interesting, and only come back together and work on what's most promising towards the end of the challenge. And that works quite well. Like, we went breadth first initially and then depth first once we figured out what was working and what was not. And we had maybe weekly meetings where we discussed our progress and did brainstorms. Oh, what makes a waypoint? So this is what the data looks like, and it's a trajectory. So you need to make predictions at a trajectory level, which is a collection of waypoints. And a waypoint is a timestamp together with a position in the building. So both a building, a floor, and an XY coordinate.
Okay, so Tom, can you hear me?
Yes.
Perfect. Okay, so I was just thinking maybe I could ask you some questions, not specifically related to this particular challenge, but in general. So can you explain how is your development process in general? Like, do you set up a quick baseline and then try to iterate on it and go to the best? Or in general, would you go forward reading through the public kernels and then building upon them?
So that was partly divided. I think Ara did a lot of work on keeping up to date with the public kernels and try to extract those IDs and implement them into our validation set. And it was very important to get something that worked end-to-end early on. So you'll see here that after week 2, we were able to make a submission. And after week 6, we pretty much had our final solution from which we only had to iterate. Does that answer all questions?
I see. So it's a combination of both. So you try to set up a baseline as quickly as possible, and then your teammates were looking around at the public kernels to make sure that you don't miss out any crucial information. Is that right?
Yeah, actually, Dimitri was mostly exploring the deep learning approach, and I was working on the engineering approach. And I think Ara did a lot of work on the geometry of the space, like trying to extract the different corridors as well as possible, and combine that with the Wi-Fi modeling. Yeah, and it turns out that we used all components in the final solution.
Yeah, okay. And so I'm going to check the YouTube comments.
Feel free to chip in, Ara or Dimitri, if you have some additions.
So I'm going to read out a question from Dirk. Did all the competition contributions make predictions consisting of a small number of waypoints, or was it some people tried to predict more granular trajectories? So this is a question in general about other teams as well, I believe.
No, the task was to predict like at the granularity specified by the organizers. So we were given these 626 trajectories, and they had these 10,000 timestamps at which you had to predict. So if I interpret the question correctly, there was no choice. Everyone had to make predictions at the same granularity.
And then Jan wants to ask, did you use an accumulation of the gyroscope and speed values?
I think this is really a question for Dimitri, since he modeled that data. But I would assume that it was just fed in to the neural net at its lowest frequency.
Yeah,
at its highest frequency, yes, so without aggregation.
Dimitri, would you like to add something?
Yeah, basically to reconfirm what just Tom said, we didn't explicitly aggregate the recordings, but we constructed a neural network, LSTM, which did it basically implicitly with some internal error correction, I believe. So we didn't use any numerical procedures, just fed the neural network all the data and it did all the work. I believe we had a comparison of the accuracy of the neural network versus numerical integration, and neural network was way more accurate in the end.
And in general, would you like to comment on the fact that you figured out that the engineering approach was much stronger than the neural network approach? But what would you like to, did you expect it to happen? Because all in the news, what we see is neural networks beat this, beat that, and things like that. So
I think it was because this was essentially a discrete problem. And because we heavily exploited this discreteness of the problem through the discrete search. If it had been a continuous optimization problem, then I think the two would be competitive.
The interesting thing is many of the other teams tried to use purely continuous or continuous with discrete. How did you determine that discrete is the way to go forward?
So actually what most teams did was they did continuous optimization, let's say the deep learning approach, and then some discretization at the end. They would convert these continuous optimization to the nearest discrete points. And what we did is we sort of skipped this continuous optimization part and went straight to the direct discrete optimization. And it's obvious that direct discrete optimization is better if your solution really comes from a discrete grid.
Yeah, it does make sense. And out of curiosity, I read through many of your GitHub code repositories. I was just wondering, I saw in many of the competitions you have used some R scripts. So and even in this one, you had some R scripts in them. So how do you develop in general?
Yeah, this is something where I would disagree with my teammates. I would always try to convince them to use R, but to no success. I think R is still superior in terms of data wrangling and visualization. As soon as you care about performance or neural networks, then yeah, sadly R breaks down. So how will Microsoft Research productionize our solution? I think it's impressive, but it's of course, not very useful to know that someone has to be at one of the grid points. That's sort of what makes it hard to productionize it. We really did love things like this leaderboard probing, which were optimized for like this competition and not so much for real world like performance. So I think, yeah, I'm not sure if this will be productionized, but if they were to do it, I think the key components of our approach are threefold. So it's the optimization. There is our relative movement models, which are excellent. I think this could be productionized. And then the third key component is our additional waypoint grid. So I think what would really transfer easily is this excellent relative movement model.
So Tom, I wanted to ask you some questions outside of this challenge itself. I'm sure many of them in the audience would like to hear more about that. Like, would you like to explain how do you what kind of I saw you are interested very much in reinforcement learning as well. So what kind of infrastructure do you use to build? Like, do you work locally and then run it on Kaggle servers, or do you rent servers from AWS or something like that? How do you go about doing this?
I would say I try to collaborate with Dimitri, and he does his magic. So it's really a question for you, Dimitri. You're much better at scaling things up.
With the reinforcement learning challenges, yeah, the infrastructure setup was a separate challenge for us, I would say. In this competition, computational resources were not kind of a key player, so everyone developed locally, basically, and we just merged the results, and it was easy to segregate tasks. So one person could produce a model to fit Wi-Fi data and shared just the outcomes. With reinforcement learning, the challenge which Tom mentioned in the beginning, where we had to construct an agent to play football, this one was quite difficult to set up. For instance, I failed to install all the dependencies on my local machine just because I had a different version of Ubuntu not compatible with the library requirements. So we ended up installing everything in Docker containers and using as many machines as were available for us. So we had a couple of machines in the cloud. I had 2 machines personally, Tom another one. So we had to create kind of a workflow where we install Docker, create Docker images, install the dependencies, and trigger the scripts. So pretty much meaning that we had to automate the full pipeline from beginning to an end in order to add or remove machines from the experiment. So we ended up having a setup where we had everything encapsulated and scripted. We had an S3 storage to share, to dump the results and to pick them up to see the progress. So it was the whole different type of a challenge of setting it up. But I would clearly encourage everyone who's competing to try to automate as much as possible since the very beginning, because it can save you a lot of time after that.
Thank you very much, Dimitri. That was really clear. Like in general, what would you? I'm gonna check the YouTube comments. Yeah. Okay. So Matthias wants to ask, how much time in total did you and your team spend at solving the challenge? Did you plan on the time? Would you spend on this, or did you just figure out in the way or something like that?
Yeah, it was full on. I think we all spent almost all our free time. At least that's what I think. And for me, it was a bit more than for the others. But like as soon as you're getting traction and as soon as you're making progress, it's hard to stop. And I think, like, I was almost treating this as a full-time job. Of course, yeah, it's easy to get addicted. And I did plan on the time to spend on this. Like, it looked like something which could easily keep us busy for a couple of months.
Yeah. So Sebastian wants to ask, what are the good challenges that you would recommend for a data scientist with 3 years experience?
So I think you want to mix like your own coding with learning from the best solutions. And I would recommend to start working on historical challenges, like the ones where the best solutions are known and where the code is shared and where you sort of maybe peek at the public kernels, the public code, start from there and try to do as well as possible, and then compare what you ended up with the best solutions. This allows you to iterate faster, get more experience more quickly, and then there's also great value in competing in a live competition and just join in on the discussions and yeah, try to beat us. Like, and what competitions are good? I think like all of them are good. Like, yeah, just whichever, use the Dimitri rule, whichever excites you, try that.
Yeah. So like this question is probably to all the teammates. I would like to hear from all of you. What's the key Sam wants to ask, what's the key takeaway you bring or not bring to your daily job of building AI products? Like your daily job is also doing machine learning, and what do you learn from Kaggle and how do you transfer it to your daily work?
Is this one you want to take, Ara or Dimitri?
All of us. I can do my take quickly. So I mostly work on the engineering side. So for instance, Dimitri's talk about automation. That's often what I do in practice, not Docker, but automate as much code as possible. So for me, it's kind of getting the opposite, getting the focus on accuracy, getting the focus on like what approaches will solve this problem better than we currently do, better than what's standard out there, better what's not state of the art, but maybe more tailored to your approach. All of this brainstorming around performance, because the engineering side, I already do that every day. So don't learn too much on that side.
I would say personally, I try to turn my job into a Kaggle competition, typically, where I try to like frame a problem which overlaps in business value, which is still a Kaggle competition. So where, but maybe where the metric is a bit different, where you also care about resources and not only about the final performance.
Yeah.
What I can add to this is a lot of learning about what works in which circumstances, because often you're facing a new challenge with regards to type of the data, with regards to the problem you haven't seen before. And what Kaggle helps me a lot is to gain confidence with regards to thinking what to try first. Of course, you never know upfront what exactly will work best, but to get some logic of what can work and what you should try. And more importantly, try to understand why. So whenever you take a new challenge, whenever you get to a good solution or you see someone else getting a very good creative solution, try to understand why it works this way, because it might be really applicable to your daily challenges or to some tasks that you will have to solve in the future you haven't solved before.
Yeah. That was indeed very good to hear. One question I'm sure many of the audiences would like to hear from you is, what would be your advice to go ahead to succeed in a competition, like maybe end up in top 5% or something like that? What would be your key advice?
I think Dimitri is the biggest Kaggle champion here, so this one is for you.
Okay, thank you, Tom. My typical advice here doesn't sound like advice, just a statement that whenever I try, in 90%, maybe more, it fails. So it is okay to fail. It will most of the time happen, but every time you fail, you learn something, you move on. So the advice I can give, not to give up when you're failing, because everyone does. And the whole Kaggle challenge is about learning from mistakes, moving on, and iterating through new ideas over and over, learning, and in the end succeeding. So just don't give up whenever you make a mistake. Just learn from it and move on. This is what is happening with absolutely everyone on Kaggle.
Except Ara, he did one competition and he won it.
I cheat by having the best teammates.
And we are close to the end of the session, so I would like to ask, would you like to share, like all of you have done several competitions, and you have, I know many of the Kaggle grandmasters have their own tricks. Would you like to share one trick that you have never shared in public ever, that probably the Belgian data science community could get benefited out of it?
I don't think there are any tricks, to be honest. Like, we are sharing everything. All of our code is shared. We're given presentations as much as we can. You need three things. You need skills, and that comes from hard work. You need to put the time into it, and then you need some luck. Like, it's always relative to others. Yeah, I don't think there are any secrets to give away, since we have already given all of them away.
Okay.
Yeah, I think it's the main secret is that there is nothing secret and everything is out there. You just need to read it, try it, grasp it, and learn from it. Yeah. So there are no secret scripts or secret ideas. Everything is shared, and every Kaggle competition winner shares the concepts, the code. So you're free to learn everything, and just don't think that there's something secret you're missing. Just keep trying.
Okay, I hope you can hear me. Thanks everyone. Thanks Tom. Thanks to the full panel. We will be always.
Tom got disconnected.
Bye bye.